Hey folks. So because of the power outage, class on Friday was just a little bit broken up. So I realized that could have affected how people paid attention to the information. So I just wanted to take a minute to just kind of redo what Dr. Viv did in class, which was derive this equation for the centripetal acceleration for uniform circular motion. So before I start any derivation, I want to take a minute to kind of think about what direction the centripetal acceleration is in. So this is something that you can actually model very easily just with whatever you have lying around at home. If you have like, a shoestring or a necklace or a hoodie or something, you can take one end of it in your hand and you can kind of start making circles with your hand, and you can, whirl it around your head in a circular motion. And what I want you to notice is that when you're doing that, when you have your hand and you're whirling this thing around in a circle, your hand is not like moving along the entire circumference of the circle, right? Your hand is kind of staying in the middle, and it's making little circles because you're having to exert forces on it. But it's staying in the middle. And that's important because your hand is the thing that's exerting the force on the hoodie or the shoestring or whatever you're twirling around. And it stays in the center of the circle that the object is making. And that's the direction that the centripetal acceleration is always in. It's always pointing towards the center of the circle. And this makes sense for a few reasons. First of all, if you think about like a particle moving along just this circle that I've drawn here, its velocity at any point is going to be the line tangent to its arc, its motion on the x-coordinate. So its velocity is always going to be tangent to the circle as it moves around. And if you're going this way, but you have to end up turning and going this way, you can't be accelerating that way, because then you keep going that way, and you can't really be accelerating that way either, because then you would just slow down. You have to kind of be accelerating this way so that you can make that turn around the circle. And it also makes sense if you just think about like thinking about those carnival rides with the swings, and you like go in the swings and they like, I don't know, whip you around really fast. What direction are the chains pointing? The chains of all the swings converge in the center of the big metal circle that they have. And that's because you have to have the force pointing towards the center of the circle in order to have circular motion. So centripetal acceleration always points toward the center of the circle. And then the other thing I want to do before I derive anything is I want to take a moment to talk about notation. So Dr. Viv used this omega naught on the board. And omega naught is a velocity. It's an angular velocity. And we're going to talk about it more when we do like proper formal angular motion after we finish translational kinematics. But it is just a velocity. The only difference is it's an angular velocity. So instead of saying I'm moving this translational distance meters per time, I'm saying I've moved some angular distance. So I've gone from theta equals 0 to maybe theta equals 25. So I have radians per second, or degrees per second, or sometimes omega naught is expressed in revolutions per second. So yeah, that's all it is. It's just a velocity. It's just an angular velocity. So now we can get to deriving centripetal acceleration. And what we're going to do is we're just going to use our calculus definitions of position, velocity, and acceleration. Those are the ones that say that velocity is equal to the derivative of position over time, and acceleration is the derivative of velocity with respect to time. And these are on your equation sheet. These are the same calculus definitions that we use to derive the constant acceleration kinematics equations, if you remember that. So we can use that. And we're looking for acceleration, so I guess we're probably going to start with position and work our way up, just keep deriving. So we will. That's what we'll do. And position is going to look a little different because we are moving around a circle. So I can't really say like the way we did with constant acceleration, like I'm starting here and then I'm moving blank meters in the x direction, because I'm not always moving in the x direction. My direction is actually constantly changing as I am going around the circle. So what we have to do is we have to express this as a vector. But that's not actually going to be too bad. And the reason that's not going to be too bad is because we are moving in a circle. So one thing that never changes is the radius, right? As we're moving around the circle, we're staying the same distance away from the center of the circle, because that's the definition of a circle. It's the locus of points that's equidistant from a center point. So that means that if we take this to be 0, 0, which is a good thing to do, and we have any point on the circle x, y, we can find the coordinates of this point because it's just trig. You know, this point has a hypotenuse r and some angle theta from the horizontal. So the point x, y is going to be r cosine theta, r sine theta. And that's your trig right triangle geometry that's going to keep coming up throughout this class. So that's what I'm going to do. I'm going to write it as a vector. And Dr. Viv uses the vector r. I think that's a good idea, just to not get it confused with x or y. And the vector r is going to be r, big R, the radius, cosine theta I hat, which just means in the x direction. That's the x component of the vector, comma, r sine theta j hat. And this is just a way to express a vector. It's a coordinate point, and you're assuming that the vector has its tail at the origin. So the vector has its head or its endpoint at this point on the coordinate plane. Okay, so that's my position, and now I just need to derive this twice to get acceleration, and then I'm kind of good. The only complication is that this radius vector, or not radius, this position vector, I should say, it's in terms of theta. It's not in terms of t. And we can see from these calculus equations here that we have to derive with respect to time. So that's not a huge deal. It just means that we're going to have to use the chain rule. So I'll write that up here just as a reminder. The chain rule says that if you have like f of x as a function, then df over dy, for example, is going to be equal to df dx times dx dy. And don't tell the mathematicians this, but just cancel out the x's. That's how I think about it. Us physics majors think about we treat derivatives as fractions. So that's the chain rule. So we're going to have to use that. Not a huge deal. So let's do that. Let's derive r with respect to time. And we're going to get, first of all, I'm going to move this r to the outside, this big R, this radius, just because it's easier. I'm going to say it's r times cosine theta I hat, comma, sine theta j hat. And you can do that with vectors. So now I'm going to derive it. And I'm going to say the r stays outside because it's just a constant. It's like a coefficient. And now I'm going to derive the vector components. So I'm going to have to derive cosine theta with respect to theta first, and then multiply it with the derivative of theta with respect to time to do the chain rule. So the derivative of cosine theta with respect to theta is negative sine theta. And the derivative of theta with respect to time, I don't know what that is yet. Well, I do, but I'm not going to tell you yet. I'm just going to write it as d theta dt. I hat. Same thing for j hat. Derivative of sine with respect to theta is cosine theta, and then d theta dt. J hat. Cool. That is my velocity vector. And now we're going to address this d theta dt, because it might seem like we're in a bad place at this point because we don't know what d theta dt is. But we actually do know what d theta dt is, because theta is in radians and t is in seconds. So this is a change in an angle per a change in time. So it's a velocity. It's an angular velocity. So this d theta over dt is omega naught. So let's write it like that. This is a factor of both vector component, so I'm just going to bring it to the outside, and I'm going to say that v is r omega naught times negative sine theta I hat cosine theta j hat. Cool. Now we just have to derive this once again to get the acceleration. So we're going to have to use the chain rule again, but we're really good at that at this point. So we're going to say that dv with respect to time is equal to, these are just coefficients, so they're going to, again, stay on the outside, r omega naught, times, now we're going to derive negative sine theta with respect to theta, which is going to be negative cosine theta, times d theta dt, I hat, comma, derivative cosine with respect to theta is negative sine theta, d theta dt, j hat. And that's my acceleration. I'm going to simplify it a little bit because this d theta dt is still just omega naught, so I'm going to bring this out to the outside. That's going to make the omega naught squared. I'll also bring the negative 1 to the outside. So what I'm going to get is that the acceleration vector is negative r omega naught squared times cosine theta I hat, comma, sine theta j hat. And at this point, this should be looking kind of familiar because I have a cosine theta here and a sine theta here, and I've got an r over here too, out in front. And r times cosine theta I hat, comma, sine theta j hat, that's our vector. That's our position vector. So I can actually rewrite this, and I can say that a is equal to negative omega naught squared times our position vector. Okay. So that is the answer, like that is the acceleration, but it's not super useful for us as like physics majors using this formula in the future to have something in terms of omega naught squared and the vector r. What we're going to want is like magnitudes, things we can measure. So that's what we're going to do. We're going to convert this all to magnitudes. So the first thing we can convert to a magnitude is r. So what's the magnitude of the radius vector? Well, you can probably just look at the picture and figure out that it's big R. But we can also do it mathematically. So the magnitude of a vector is that's just the Pythagorean theorem. It's the x component squared plus the y component squared all under a square root. So we can say that the magnitude of r is equal to the square root of the x component, which is r squared cosine squared theta, plus the y component, which is r squared sine squared theta. This r squared is a factor of both of these, so I can bring it to the outside of the root. When I bring it to the outside of the root, it drops a square. So this is r root cosine squared theta plus sine squared theta. And at this point, you should recognize that this is the most important trig identity, which is cosine squared theta plus sine squared theta is equal to 1. So this is just r times 1, so this is r. So kind of proves what we already knew. So I can write this as acceleration is negative omega naught squared times r. And that's a little better because r is something that we can measure, but I still don't like the omega naught. I want to get rid of it because I think it's ugly. So what I'm going to do is I'm going to find the magnitude of this velocity vector. Because if we think about something moving around in a circle, and we want to find the acceleration towards the center, the velocity that it's going around the bend, that's something we can measure. So maybe we can get omega naught in terms of velocities. So now the question is, what is the magnitude of this velocity vector? And we're just going to do the same thing. We're going to say that the magnitude of v is equal to the square root of the x squared plus the y squared. So that's, I'm just going to, once again, distribute the r omega naught out into both components, and that's going to be the square root of r squared omega naught squared, negative sine theta, all squared is just, the negative cancels out, so it's just sine squared theta, plus r squared omega naught squared cosine squared theta, And you should be recognizing once again that we have this sine squared theta plus cosine squared theta, which is just 1. So this is going to simplify to the square root of r squared omega naught squared, which is just r omega naught. So that's the magnitude of our velocity. So if v is equal to r omega naught, then omega naught is v over r, right? Just dividing both sides by r. So let's put that back in here. Now we have a, and I shouldn't really be using the vector sign anymore because we've converted things to magnitude, so this is just magnitude a. A is equal to negative omega naught squared, which is v squared over r squared, times r. Or a is equal to v squared over r. This is your centripetal acceleration equation. This is what you need to remember. Now, I dropped the negative. Why did I drop the negative? I did do it on purpose. This is how it's written on your equation sheet. This is what you're going to need all the time, every time. The negative that pops out in this equation tells you that the acceleration always points towards the center of the circle, right? Because your vector quantity in this equation, this vector equation that we have up here, is a vector is equal to negative omega naught squared r vector. This r vector points outwards from the circle, right? If we define a circle like this, the radius vector points outwards. That's why you put an arrow there. But the acceleration points inwards, and that's why we have that negative sign there that pops out in the equation. So the math does actually tell us what direction the acceleration is going in. We drop it when we write the equation because we know, as physicists and smart people, that the acceleration when you're moving in a circle always points towards the center of the circle. So all of this is a derivation. You are never, probably ever, going to have to do this derivation. What you are going to have to do is you're going to have to know this equation, because you're going to be given a problem where you're like going around in a circle and it has radius 10 and they want to know how fast can you go without exceeding 30 Gs, and you're going to have to figure out, okay, 30 Gs is 30 times 10, so 300 is your A, which is equal to something v squared over 10, so v squared is equal to 3,000, and your maximum speed is the square root of 3,000 meters per second squared, which is really fast. Those are the types of questions that you're going to have to answer with this, and this is the equation that you're going to need with that. All right, so you guys can let me know if you have any questions. I hope that this cleared a little bit up if you guys happen to be confused about the lecture. And I will see you all on Monday. Have a good weekend.